Hello students, today I am going to explain the last topic of first unit IR spectroscopy, instrumentation and application. First we discuss instrumentation. Generally the IR radiations involves the vibrational motions of the molecule. IR spectrum is a result of vibrational transitions, and this results in the characteristic absorption spectra. The working range of IR spectrophotometer is from 400 to 4000 centimeter inverse. This is the wave number region, which is generally known as vibrational frequency. And IR spectroscopy is generally used for the determination of functional group. So by the detection of functional group, it is helpful in the chemical identification. So it can be a valuable tool for the determination of organic and to some extent inorganic structures. First, we discuss the normal instrument of IR. Normal spectrophotometer of IR spectroscopy, which is more or less similar to UV visible spectrophotometer. But the main difference is the light source and detector. In UV visible spectrophotometer, the light source provides ultraviolet radiation or visible radiation or both radiation. But in case of IR spectrophotometer, the light source only provides infrared radiations. This is the block diagram of IR spectrophotometer. This is light source. After from the light source, light is first converted into monochromatic light. After that, this monochromatic light is divided into two beams. First is passing through the sample and another is passing through the reference. And during the detection, the reference beam is subtracted from the sample beam. So only we get the amount of light absorbed by the sample. First, we discuss the light sources of IR spectrophotometer. Light sources must produce IR radiation, and we cannot use glass, since glass to some extent it is IR radiation absorbing. Different light sources can be possible. First is Nernst glower. Nernst glower is generally made up of zirconium, cerium or thorium oxides. These rare earth metal oxides, when heated, they produce radiations which are similar to black body radiation. And the wave number range of these radiations is from 670 to 10,000 centimeter inverse. The problem with or the limitation with Nernst glower, it needs good current control, or sometimes upon overheating it can be damaged. Another light source is glower. Glower is similar to Nernst glower light source, but it is made up of the rods of silicon carbide, and it can also be used for the similar IR range. Third can be incandescent wire source. In this, nichrome or rhodium tightly wound wires are used, or they are also working on the same principle as Nernst glower. That means upon heating they produce radiation, but their intensity is lower than the previous two light sources. But advantage is that it has longer lifetime. Another light source which can be used for IR spectrophotometer is carbon dioxide laser. Carbon dioxide laser is the mixture of gases like 70% helium, 15% carbon dioxide, and 15% nitrogen. When a fixed voltage is placed across these gases, this voltage excited nitrogen molecule and to higher vibrational levels. So this excited nitrogen populates the asymmetric vibrational transitions through the carbon dioxide collisions. much more intense than black body sources. Other sources that can be used in light IR spectrophotometer are mercury arc. It can be used for a far IR, and tungsten lamp. Tungsten lamp is generally used for near IR region. Another part is detector. The first detector which can be used is thermal detector. In thermal detector, here you can see there are two wires of two different metals, and these two wires fused together at the ends. When these wires heated, metal, since they are made up of two different metals, so metals heat at different rate. So this will generate a potential difference, and this potential difference depends on the temperature. Usually these wires are made with blackened surface placed in evacuated tube with window transparent to IR radiation. Another is photoconducting detector. Photoconducting detector is this thin film of semiconductor like lead sulfide on a non-conducting glass surface. Here you can see in the figure at the bottom there is a glass, and upon the glass there is a non-conducting semiconductor thin film. Absorption of light by semiconductor moves from non-conducting to conducting state, and this decrease in resistance or which increase in current. Its range is 333 to 10,000 centimeter inverse. It can be worked on room temperature. This was all about the normal IR spectrophotometer or conventional IR spectrophotometer. The alternative or the modernization or advanced form of conventional IR spectrophotometer is Fourier transform IR. Fourier transform IR is based on the principle of splitting of light, or we can simply say that the beams goes to two other mirrors reflected by central mirror and recombine and pass through the sample to detector. There are two sides mirror, one fixed and other movable. This is the block diagram of FTIR spectrophotometer. In this, the detector used is deuterated triglycerine sulfate or mercury cadmium telluride. The basic principle of Fourier transform spectrophotometer is totally based on physics concept, but we can simply say that Fourier transform is a technique which can convert the frequency domain spectrum into time domain spectrum. This is the main advantage of FTIR spectrophotometer. In general words, in conventional IR, 400 to 4,000 centimeter range of IR during the scanning or during the irradiation, this range of light is can excite the vibration one by one. That means we cannot irradiate the molecule by whole frequency of radiation. Suppose from 400 we increase the light frequency or wave number of the light gradually, and one by one the vibration will excite it, and then we get the absorption P. But in case of FTIR, at a time the molecule is irradiated by a pulse of light that contain all the frequencies from 4,000 to 400 centimeter inverse. So all the transitions are excited simultaneously. So the spectrum obtained is more sensitive than conventional IR. So this is the main advantage of FTIR. Other advantage, it is time consuming. There is, since it is based on the principle of averaging, so the signal to noise ratio is always less than the conventional IR. The resolution of the spectrophotometer is higher. But the disadvantages of FTIR as compared to normal or conventional IR. It is based on the single beam, requires collecting blank, and can't use thermal detectors. And the detectors used in the FTIR are comparatively of slow working. So in normal IR, scan through frequency range, and in FTIR, collect all frequency at once. That is known as pulse technique. In pulse technique, all the excitations occur simultaneously. Sample holder and sampling of substances. By IR spectrophotometer, we can analyze solid, liquid, as well as gaseous sample. The intermolecular forces of attraction are most operative in solid phase and least in the case of gas. Always the medium or the solvent or the background used for the IR spectrophotometer should be IR transparent or low absorbing. The sample of some substances shows shift in frequencies of absorption as it passes from solid to gaseous state because of intermolecular forces of attraction. In some cases, additional bands are also observed with the change in state of the sample because of the sometimes change in hydrogen bonding. Important to mention that the state of the sample and solvent for scanning in IR region. For correct interpretation of spectra, it is most important thing. Now we come to the applications of IR spectroscopy. First is the identification of the substance. IR spectroscopy only give an information about the functional group present in the molecule. We cannot detect which compound is present in the molecule, but present in the sample, but we can detect the functional group present in the molecule. If we have the two spectrums, two IR spectrums, no two spectrums will have identical IR spectrum. Even they have same functional groups. The difference is because of their skeleton. Suppose in case of alcohol and in two different alcohols, functional group is same OH, but the molecular skeleton is different in methanol CH3 and ethanol CH3 CH2. So the skeleton will be different. So the absorption or the spectrum obtained in the fingerprint region is definitely different. So this fingerprint region is helpful to identify an unknown compound. Here you can see two different alkenes whose molecular formula is same, but they are chain isomers. First compound is 2,3-butane and second is they are not having same molecular formula, they are different but same alkanes. This is 2,3-butane and it is only 2-butane. All in the molecule only there is carbon-carbon bonds, carbon-hydrogen bonds. But since in the first molecule the skeleton is different, one CH3 group is extra, so here you can see the fingerprint region of both the spectrum is not similar, whereas the functional group region is similar. So on the basis of fingerprint region, we can identify the molecules or spectrums that are of similar compounds or different compounds. Second is computer search system. Computer search system, nowadays all the spectrophotometers are generally software oriented, and these softwares have some libraries. Libraries match during the sampling, the compound matches with the library already present spectrum in the library. If it is similar, then software will produce a percentage matching. Here you can see the lower spectrum is collected from the library and another is scanned or unknown sample. After the scanning, software will produce the result that there is 90% or 100% matching between the library spectrum present in the library and the scanned spectrum. If it is more than 70%, then we can sure that the scanned compound is similar to the library result. Next, determination of molecular structure used along with other spectroscopic techniques, since only it gives an idea about the functional group present in the molecule. Identification is done on the position based on the position of absorption band in the spectrum. For example, carbonyl group produce absorption spectra approximately at 1700 centimeter inverse. If there is no peak in between the 1650 and 1800 centimeter inverse, then we are sure that there is no carbonyl group present in the molecule. This is known as the negative interpretation. That means the such group is 100% absent in the molecule. Third is the study of progress of reactions. Observing rate of disappearance of characteristic absorption bands in reactants or rate of increasing absorption bands in the products of particular products. Suppose in the reaction, during the reaction, as the amount of product will increase, the stretching bands or absorption bands observed due to the product molecule will have higher peak area or higher absorption value or transmittance value. It is also helpful in the detection of impurities. It can be determined by comparing sample spectrum with the spectrum of pure reference compound. Or it can be used for the laboratory synthesized, to compare the laboratory synthesized compound and the pure compound. Detection is favored when impurity possesses a strong band in IR region, where the main substance do not possess. Isomerism in organic chemistry. Geometrical isomerism. In case of geometrical isomerism, trans isomers give a simpler spectrum than cis due to symmetry. Generally the cis molecule has bulky, if it is bulky group, because of steric crowding, the spectrum shows different bands. It is also helpful in the identification of conformational isomers and tautomers. Here you can see thiocarboxylic acid. Thiocarboxylic acid, one is having SH group and another is having C double bond S group. In tautomerism, in the equilibrium, one tautomer is predominate. If we are getting carbonyl band in the IR spectrum, then we can say the C double bond O, this tautomer is predominates or maximum present in the molecule. Functional group isomerism. Similarly, molecules having the same molecular formula but different functional group. Here we can take the example of diethyl ether and ethanol. If we obtained a broad band in between 3000 and 3500 centimeter inverse, then we are 100% sure then the molecule has OH stretching. If it is absent, then the molecule will be ether, and the ethereal functional group is or C OC or C single bond O stretching is generally observed at 1200 centimeter inverse. IR spectroscopy is also useful for the determination of for inorganic complexes. In inorganic complexes, the difficulties are generally because of high mode of vibration, lower symmetry of complexes, and sometimes because of the formation of chelates. It is also helpful in the determination of shape of symmetry of molecule. For example, nitrogen dioxide can be present in the linear form or band form. Nitrogen dioxide, if the molecule is linear, we get 2 bands. If the molecule is band, then we get 3 bands. The actual spectrum of nitrogen dioxide shows 3 peaks. So we can conclude that nitrogen dioxide is not a linear molecule. Similar, on the lines of this principle, we can determine the structure of more molecules. The main advantage of IR spectroscopy is the identification of functional group due to the presence of functional group region. Here you can see the spectrum of butanone. Butanone shows the sharp peak at 1750 centimeter inverse because of this aliphatic ketonic group. Similarly, another aliphatic alcohol 2-methyl-2-propanol, it shows broad OH stretching band at from 3000 to 3600. IR is very much susceptible for the detection of water in the molecule. If in the molecule OH stretching is present, that means molecule has some amount of moisture. These are the more applications of IR spectroscopy. Thank you. This was all about the instrumentation and applications of IR spectroscopy.